Welcome back to another explainer. Today, we're tackling a topic that literally every single computer user has experienced firsthand. It's something that software developers absolutely dread and, well, let's be honest, every user has screamed at their screen over at some point. I'm talking about software dev. We're going to explore exactly how computer scientists and programmers evaluate algorithm efficiency to keep our applications alive, responsive, and functioning flawlessly, even when they're pushed to their absolute limits.
Okay, let's dive into this. Have you ever been right in the middle of a crucial task? Like, maybe you're trying to render a super heavy 4K video for social media, or you're loading a massive dataset for a computer science project, and your app just completely freezes. The cursor turns into that dreaded spinning wheel, the screen grays out, and you're just stuck waiting. You might be wondering, what exactly is happening under the hood here? Why does software suddenly just halt when data gets too big?
Well, to really understand this, we need to look at what happens when a program simply cannot cope with the scale of a task. We have some classic, frankly painful, examples of this. Well, today it might be a massive cloud spreadsheet crashing your entire browser. Imagine the classic example of a text editor, something like Notepad. It can successfully load 1,000 pages just fine, but then it can only spell check 1 page per minute. Or picture using an old-school image editor that takes literally a full hour just to rotate a single photo 90 degrees. No way, right? When this happens, the program is as good as dead. The algorithms powering these features are totally failing to handle the input data efficiently.
Now, what's really interesting about this is the contrast in how we actually measure that performance. It is incredibly tempting to just grab a stopwatch and measure the actual execution time in seconds or milliseconds. But as you can see, this is highly machine-dependent. The exact same code is going to run way faster on a brand new gaming rig than on a 10-year-old laptop. Because of this, computer scientists use time complexity. Time complexity doesn't look at the clock at all. It counts the absolute operations or steps a program takes. Think of absolute operations as the literal number of calculations the computer's brain has to make. This makes our measurement entirely machine-independent.
Let's actually test that logic with a quick scenario. Say you run a program on a slow, older PC, and it processes 10 items in 0.5 milliseconds. Then you run the exact same program on a multi-million-dollar supercomputer, and it processes 10,000 items in just 0.2 milliseconds. So, did the algorithm actually get better? Absolutely not. The hardware changed, the system load changed, but the fundamental mathematical logic remained exactly the same. This totally proves that raw execution time is just not a robust measure of an algorithm's actual efficiency.
So, to get a true objective measure, we use a numerical function represented as t of n. Let's break that down real quick. The t stands for time, or the number of computational steps, and n represents the size of our input data, like the number of pages in that text editor or the millions of pixels in that image. By using this function, we shift our focus entirely to the rate of growth. We really want to know, as n gets larger and larger, how fast does the number of computational steps increase? Does it grow linearly, step by step with the data, or does it spike exponentially and crash the entire system?
In practice, calculating every single step of a program leaves you with a really messy mathematical function. To study growth efficiently, we use a technique called asymptotic analysis to reduce the function down to its most important part. First, you write out the messy function. Let's say f of n equals n squared plus 3n. Step 2 is where the magic happens. You just drop the constants and the lower order terms, meaning the parts of the math problem that just don't grow as fast. If your input n is a million and you have a million squared, adding 3 times a million barely makes a dent, so we just ignore it. That brings us to step 3, where we identify our dominant term, which here is n squared.
So the absolutely crucial point is that this dominant term, n squared in our little example, is the only thing that truly matters when determining how an algorithm will perform at scale. As data size approaches infinity, this dominant term dictates the steepest increase in processing time. It's the core boundary that tells us whether our software will gracefully handle millions of users or if it's going to suffer a sudden, freezing death.
Now, while math gives us the dominant term, how does this actually play out with real data? Let's bridge this abstract math to reality by comparing scenarios to a search analogy. Imagine searching for a specific name in a massive old-school phone book, or for a more modern equivalent, writing code to find one specific username in a database of millions. The best-case scenario? That's finding it immediately on the very first page or with the first user profile you check. It takes minimum steps. The average case is finding it somewhere in the middle. But the worst case?
That happens when the name is on the very last page, or maybe it's not even in the database at all, forcing your code to take the maximum possible number of steps to verify. To communicate these different scenarios clearly, computer scientists use specific mathematical shorthand called asymptotic notations. The absolute most common one is big O notation, written as a capital O. Big O is the formal mathematical method for expressing the upper bound of an algorithm's running time. Think of the upper bound like a ceiling. It represents the absolute longest possible amount of time an algorithm can take to complete for a given input. Basically, it measures the worst-case time complexity.
You can contrast that with omega notation, which is represented by the Greek letter omega. This notation formally expresses the lower bound of an algorithm's running time. So think of this as the floor. It measures the best-case time complexity. This tells you the absolute minimum amount of time or steps needed if conditions are absolutely perfect, like getting incredibly lucky and finding that name on the very first page of the phone book. It is a mathematically guaranteed minimum that just cannot be beaten.
And finally, we have theta notation. Theta is the formal way to express a tight bound. You use this when an algorithm's running time is sandwiched precisely, meaning the ceiling and the floor are essentially the exact same in terms of their growth rate. When you can express an algorithm using theta, you have a highly precise understanding of its exact complexity, regardless of whether you get lucky or unlucky with your input data. Okay, so what does this all mean? Let's put these notations into a real-world perspective. Imagine you're a student developer or a startup founder. You've built a brand new database application and you're pitching it to a major corporate client. To guarantee your product works and close the deal, which scenario do you confidently pitch to them? The best case omega, the average, or the worst case big O? And this brilliantly illustrates the industry standard. If you pitch the best-case scenario, you're essentially telling the client, hey, our software takes 0.01 milliseconds, assuming you get incredibly lucky. And trust me, nobody is signing a $1 million contract based on luck. But if you pitch the worst-case scenario using Big O, you can confidently say, even under the heaviest load, this will never take longer than 5 seconds. Promising a lightning-fast best case is utterly useless if your software freezes for hours during a worst-case data spike.
Which brings us to our foundational understanding of why Big O wins out in the real world. Big O notation is universally favored by developers because it guarantees absolute performance limits. By always preparing for the maximum input size n, programmers safely ensure that their algorithms can handle extreme scaling. Ultimately, focusing on that ceiling, the upper bound, is what prevents our favorite apps from freezing, crashing, or suffering software death in a live production environment.
This all boils down to a core philosophy derived from these sources. A programmer always builds for the worst-case scenario to guarantee performance. Next time an application handles a massive amount of your data without breaking a sweat, you'll know it's for sure because someone ran the asymptotic analysis and prepared for the absolute worst. So, I'll leave you with this. In your own code, what worst-case scenarios are you preparing for to ensure your projects never crack under pressure? Thanks for joining this explainer, and we'll see you in the next one. Keep coding.